Okay, so in this video, I'm going to talk about our spin 1/2 particle in a magnetic field in more detail. In particular, I want to talk about the other components of the angular momentum. So the first thing to do is to solve the classical problem more explicitly, and that'll tell us how the x and y components of the angular momentum evolve in the classical case, and then we'll use that to compare to the quantum mechanical case. So I said last time that the torque on our particle will be mu cross b, or gamma s cross b. And again, I'm assuming b is still along the z direction. So if you do that and you work out the cross product, you'll get the torque has an x and y component, where the x component is gamma b sy, and the y component is minus gamma b sx. And then you can just use the classical equation of motion that s dot, the time derivative of the angular momentum vector, is equal to the torque. So this is just like F equals ma, but the angular analog. And there will be three components of this equation. So this tells us that the x component, sx dot, should be equal to the x component of the torque, which is gamma b sy. Sy dot is minus gamma b sx. And as we found earlier in the last video, z dot is 0. So sc is constant. And that's, again, because there's no torque in the z direction. Of course, sc is constant. And so this is a set of coupled first-order differential equations. And it's very easy to solve. All we have to do is take the time derivative of, say, this equation, and we get this. And this involves sy dot, so we can then plug in this equation. And then a similar thing for the sy. And we can decouple these equations. So we have two uncoupled second-order differential equations for sx and sy. And this is, if there's one differential equation you should know, it's this one. It's the harmonic oscillator. So what this tells us is that basically, if I were to draw my angular momentum vector, what it would do in time is precess around the z-axis. So sx, if we choose the initial conditions so that initially the angular momentum is all along the sx direction, and well, the sc and sx direction, then sx will go as cosine omega t, where omega is just gamma b, and sy goes as sine omega t. And so, so s will just will trace out a cone, basically, around the z-axis, and the projection of s on the xy plane, so I've drawn that here, so this magnitude will stay constant. So this will just go around and point, in different directions in the xy plane, but the magnitude is constant. So we should expect, when we solve a quantum mechanical problem, to see, when we calculate the expectation values of sx and sy, we should get a similar kind of thing. Okay, so how do we actually solve or work with the quantum mechanical version of all of this? And the way you might think it's done is, well, we're talking about three components of angular momentum now, so I can measure along, the x, y, and z axes, and I can still only get either spin up or spin down along those axes. So maybe you think that the way to, or what you need to describe your system is a measurement along each of these three axes. And so there would be 6 different, combinations. There's 2 choices. The x component of the spin can be up or down, sy can be up or down, sc can be up or down. So there's 6 possible states, and that our state would be this kind of linear combination of these basis states, where plus 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 means they're all up, plus plus minus means up, up, down, and so on. And basically this doesn't work at all. It doesn't lead you to the correct answer. So what does happen, okay, physically, it's kind of weird what happens, but mathematically, it's not difficult to describe it. So basically what is going to happen is that we can measure the x component of our angular momentum, and we can measure it to be either spin up or spin down. But those states, my states where my x component of my angular momentum is up or down, can be written as linear combinations or linear superpositions of states where my z component of the spin is up or down. So that's strange, but the motivation for why why this might be true, is that if you measure, say you measure Sx and you get spin up. And if you, classically, in a classical sense, you would think that, well, if you measure the x component of the angular momentum, that has no effect on the z component of the angular momentum. It shouldn't matter what I measure the x component. But what happens is, if you do measure the x component of the angular momentum, unless say you get it to be up, and then you measure the z component of the angular momentum, half the time you measure the z component to be up, and half the time you measure the z component to be down. And well, we can think of a state where half the time you measure the z component of the angular momentum you get up, and half the time you get down. We could have these two states, and because the coefficients of each of these kets, the modulus squared of it is 1/2, then you have a 50% chance to measure spin up or spin down. And then similarly, the same thing would happen if you measured the x component of the spin to be down. If you then measured the z component of the spin, you would get up half the time and down half the time. So this is another linear combination of kets, of my SE kets that I could get, that matches that observation. And again, we would still want these two kets to be orthogonal. So Sx plus should be orthogonal to Sx minus. So that's the motivation for having different vectors or combinations of vectors that satisfy this, is you can verify if you do these inner products, these are orthogonal states. So this is really weird. It's telling us that you only need to describe the system using either your spin z kets or your spin x kets or even your spin y kets. And once you know that, you pretty much know the other components of the angular momentum, which is very unlike the classical case. So that's confusing, but mathematically, it's not that complicated. We're just saying that if our particle is spin up in the x direction, that is equivalent to our particle being in a linear combination of our spin z kets. So if it's in a definite angular momentum state, it is not in a definite spin z angular momentum state. And that'll take some getting used to, but we'll just keep working and show how we can work with all of this. So similarly, a same kind of thing would happen with the sy kets. And I'm just going to tell you that this is how we write the sy vector. So again, if we did the same thing, if we measured sy and we got spin up in the y direction, and then we measured spin z, once again, we would get half the time it's the spin z component is up, and half the time it's down. So another state we could write that still satisfies that property, is this one. So the modulus squared of each of these coefficients is still 1/2. So the modulus squared of this one is just 1/2 times 1/2, or 1 over the square root of 2 times 1 over the square root of 2, which is 1/2. The modulus squared of this one is I over the square root of 2 times minus I over the square root of 2, which is still 1/2. So that will satisfy the observations. And then similarly, this is the same kind of one, only with the minus sign here, so that these two states are orthogonal. And again, the modulus squared is still 1/2 for both of these coefficients. So basically what I'm saying is, To describe our state, we can either write our state as a linear combination of these SZ up and down vectors, or we can write it as a linear combination of my SX vectors or my SY vectors. So they're different bases that I can use to expand my ket in. And again, it's really weird that you only need one set of bases and these aren't like independent of each other, but mathematically it's very simple. We're just saying that I have 3 different sets of basis vectors that I can use to expand my ket. So, I mean, undoubtedly it's going to be a little confusing, but in the next video I'll show you how to work with all of this, and we will compute the expectation values of x, sx, and sy using this formalism, and we'll see that it does indeed match up with the classical case.